In last class, not working. Working? It's not working? Oh, now it's working. Okay. So in last class, I kind of introduced to you two important concepts. One, I gave you the rules for drawing kinematic diagram and setting up the coordinate system. I don't know if you guys remember the rules. First rule is the z-axis to join. These are the exact same rules that are used if you use DH parameters. Second, xn intersects zn minus 1. And of course, xn would intersect zn. And third thing is the right hand coordinate. I also talked about two things. You have a revolute joint and you have a prismatic joint. You have a revolute joint and you have a prismatic joint. In the last class, we talked about something called as the forward kinematics. What is forward kinematics? Now let me define forward kinematics in a two-dimensional case. So imagine that I have a robot and this robot has one revolute joint over here. There's one revolute joint and then there is a link and I have the second revolute joint over here and then I have this link number 2. So I have this link, I'm going to call this A2, I'm going to call this A4. This axis is my x-axis. This is y-axis. So there are two revolute joints. So I need to provide two angles. And I'm going to provide two angles, something like this. This is going to be my angle theta 1. This is going to be my angle theta 2. Now, what is forward kinematics? Forward kinematics is given the values. So forward kinematics is given theta 1 and theta 2. Find x end effector, y end effector, z end effector in zeroth frame, in inertial or zeroth frame. As you can see, for this two-dimensional 2 degree of freedom system, it's a fairly straightforward problem. So what I'm going to do is I'm going to draw vertical line. I'm going to draw horizontal line. You agree with me, this is going to be A2 cosine theta 1. This is going to be A2 sine theta 1. Do you agree with me? So I have A2 cosine theta 1 and A2 sine theta 1. I need to find out the projection of link A4 onto X1 on X, and I need to find projection of link A4 on Y. Now, extremely important to note that the angle of the link 2 is with respect to link 1. Can you note that? angle of link 2 is with respect to link 1. So if I were to draw a horizontal line, do you agree with me that this angle is going to be theta 1? Which means if I were to look at the projection, this guy here is going to be A4 cosine of theta 1 plus theta 2. If I were to look at the projection, this guy is going to be A4 sine theta 1 plus theta 2. Do you agree with me? So in other words, the forward kinematics and this system, this is a two-dimensional planar robot. So this is a planar robot. So I can write down the end effector position, something like this. And remember this is extremely important. XE, that needs to be with respect to the zeroth frame. Zeroth frame is the inertial frame, the frame where robot is fixed. This frame is not moving. So the robot, other frames could move, but this frame is fixed to the ground. It's not going to move. So XE is going to be A2 cosine theta 1 plus A4 cosine theta 1 plus theta 2. YE is equal to A2 sine theta 1 plus A2 sine theta 1 plus theta 2. And ZE, since this is a planar robot, ZE is equal to 0. Everyone understood this? So what is the forward kinematics problem? Forward kinematics problem means the link lengths A2 and A4 are known because they are actually the robot dimensions. Given theta 1 and theta 2, find XE, YE, and ZE. This is the forward kinematics problem. Now please understand, forward kinematics problem will have a solution, which means I can substitute any value of theta 1, any value of theta 2, and I know that I would get XE, YE, and ZE. Everyone understood this? Now, what is inverse kinematics problem? Inverse kinematics problem, which is also called as IK problem, inverse kinematics. In inverse kinematics problem, I give you the value of XE, YE, ZE, and you have to find theta 1 and theta 2. Are you with me? So in forward kinematics problem, joint angles and link lengths are known. You have to find out the end effector position. In inverse kinematics problem, the end effector position is given and you have to find out joint parameters. It could be the displacement or it could be the angle or the rotation. Now please understand, inverse kinematics problem can have a solution. So it can have a solution. It may not have a solution. May not have a solution. A simple example is if your inverse kinematics, so if the point is outside the robot workspace, then there is no solution. Or imagine the robot is folded onto itself, then you cannot find inverse kinematic solution. So inverse kinematic solution may exist, may not exist. That is the first thing. It may exist, may not exist. You can have a single solution, a unique solution, or you can have multiple solutions. Multiple solutions. And I give you an example. So please try to understand. Same, you have a two-dimensional planar robot. Two-dimensional planar robot. And I give you an end effector position over here. This end effector position can be achieved in this configuration, or the same end effector position can be achieved in this configuration. So what you have is you have potentially two possible orientations, or the pair of two possible orientations that can get you to the same end effector position. So inverse kinematics problem may have a solution, may not have a solution. It can have a unique solution. It can have multiple solutions. Everyone understood this? Now, how do you choose which solution to pick? And this solution picking, because today I will teach you how to solve inverse kinematics problems, but please try to understand mathematically the solution that you would get from inverse kinematics problems or inverse kinematics solver may or may not be practically realizable. It means, as an example, if you look at Dubot Magician has some dead zone. Because of the physical joint limits, it cannot get to certain angles. So for that, what we do is we do something called as workspace analysis, which means we identify all the possible joint values that the robot can have. And we solve the inverse kinematics solver, or use the inverse kinematics solution. And it will give us maybe 3 or 4 angles. And out of those 3 and 4 angles, we choose the correct sequence of angles that is feasible. So this is how the inverse kinematics works. So everyone understood? Key observation here is we have to look at the rules. Any robot, when we draw the kinematic diagram, it needs to be in terms of the revolute and prismatic joints. And then when we solve the inverse kinematics problem, so to solve inverse kinematics problem, first you have to solve forward kinematics problem. Once your forward kinematics problem is solved properly, inverse kinematics problem should be easy. When I studied robotics, solving an inverse kinematics problem was a huge pain. But because you will have to understand that equations that you are dealing with, these are transcendental equations. It means even though you have two equations and two variables, those are not x and y's, those are sines and cosines, which means they have multiple solutions. So you will have to do this mathematical jugglery to find out the correct solution. But now we use MATLAB. So in today's class, I will set up the forward kinematics problem. We will solve the forward kinematics problem, and then I will teach you how to solve inverse kinematics problem using MATLAB. Everyone understood this? That's why I emailed you the script, and for my satisfaction, I'm going to rework the problem that I solved in last class. So in the last class, we had R parallel R robot. So you have this robot, you have first revolute joint. This first revolute joint is attached to second revolute joint. Second revolute joint is attached to the link and this forms the end effector. This is your first revolute joint. This is your second revolute joint. This length is A1. This length is A2. This length is A3. And this length is A4. And the first revolute joint has the joint angle θ1. Second revolute joint has the joint angle θ2. I have drawn the kinematic diagram. This is called as the kinematic diagram. I'm going to call this KD, kinematic diagram, wherein all the joint angles and joint displacements are 0 and robot is in fully stretched condition. The joints are not folded. A word of caution or an observation. Can you see that the three-dimensional robot that I have drawn is nothing but the two-dimensional robot that I have shown in the picture? Which means if our forward kinematics is correct, and if I substitute my value of A1 is equal to 0, and if I substitute value of my A3 is equal to 0, I should get the exact same answers. Do you agree with me? The three-dimensional kinematic diagram for R parallel R robot is same as the two-dimensional diagram of R parallel R robot that is shown in the figure. Step number one. Step number one, remember the rules. What is the first rule? Your z-axis should pass through the joint. Doesn't matter whether it goes up or it goes down. The z-axis needs to go through joint. The x-axis should intersect the previous z-axis. If you look at the first revolute joint, there is no revolute joint before the first revolute joint. So I would assume my z-axis and my x-axis, x0, to be like this. Doesn't matter whatever orientation you choose, that's totally fine. Now, second thing, I need to find out x1. I discussed this in last class. We have two choices. x1 can go in this direction. x1 can go in this direction. But I choose x1 to be in this direction because now x1 intersects with z0. Do you agree with me? The last axis, I'm going to treat this like x2. Now I have to complete the triad. So the triad is y0, y1, and y2. Do you agree with me? This is the first and most important step. If your axes are not aligned with the sign convention, your forward kinematics would go wrong. Now I need to set up the relationship between 0, R1. Remember, the only rotation matrix that we are going to remember is cosine θ1 minus sine θ1, 0, sine θ1, cosine θ1, 0, 0, 0, 1. Do you agree with me? A rotation matrix must be multiplied with the projection matrix. Now, in the projection matrix, what you have is projection of x1, y1, z1, projection on x0, y0, z0. So this is projection of. This is the new frame. So please note, this is the new frame. And x0, y0, z0 is the old frame. Now I want you to look at x1. Can you see x1 is aligned with x0? y1 is aligned with y0. Z1 is aligned with Z0. So I get this unity matrix. Whenever you multiply a matrix by an identity matrix, you get the same matrix. Cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. You agree with me? Now I need to write the homogeneous transformation. Homogeneous transformation is 0H1. The first 3 by 3 matrix in the homogeneous transformation is cosine theta 1 minus sine theta 1, 0, cosine sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 1, and then the last row is going to be 0, 0, 0. There will be 1 here, and here comes the most important part. I need to fill in these blanks. Now, remember, this belongs to X, this belongs to Y, this belongs to Z. So this is the relationship between the first frame and the 0th frame along old frame or along 0th frame. So please note the distance between the second frame. So this is the distance, this is the second frame, this is the first frame along X0. The first frame, this distance is A2, but that A2 is valid as long as your theta 1 is 0. So I'm gonna say this is gonna be A2 cosine theta 1. When theta 1 is equal to 0, you're just gonna get A2. This is gonna be A2 sine theta 1, and this is going to be A1. I would explain this one more time, but it's extremely important. Homogeneous transformation is one of the most fundamental matrix that you need to solve forward kinematics problem. Homogeneous transformation is a 4 by 4 matrix that encodes the orientation and the relative displacement or relative distance between the previous frame, which is the 0th frame, and the second frame in the coordinate system associated with the previous frame. So please understand, this gives you the orientation information. This is 0R1. The next 3 columns or next 3 rows, they are going to give you the distance between the first frame and the 0th frame along X0, Y0, and Z0. Everyone understood this? This homogeneous transformation encodes everything that you need to define the angular and translational relationship between the previous frame and the next frame. Now I'm going to carry out the same thing. Now I would go with 1R2. Again, please understand, our rotations are about Z-axis. So I can go through the same process. Cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2. 0, 0, 0, 0, 1. And don't forget the projection matrix. Projection of x1, x2, y2, z2. Projection on x1, y1, z1. So please note, this is projection on. This is projection off. Now, I want you to look at, can you see that x2 is going towards right? X1 is going towards right. Y1 is going towards in the board. Y2 is going in the board. Z2 is also aligned with Z1. Do you agree with me? So can I just write the identity matrix same as before? 1 0 0 0 1 0 0 0 1. And I'm gonna get cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2 0 0 0 0 1. Any questions? Now comes the homogeneous transformation. Homogeneous transformation is going to be 1H2 because I want to represent angular and translational relationship between the frame 2 and frame 1. So I would just rewrite cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2 0 0 0 0 1, and this becomes 0 0 0. And now I want you to tell me what should I write for the relative displacement or relative displacement between the frame 2 and frame 1. I want you to pay very close attention because in this particular case, it's going to be what you need to assume is that relationship should hold true for all the joint angles, which means whether theta 2 is 0, theta 2 is 90, theta 2 is 180, that relationship still hold true. Everyone understood this? One more important point, that when you are writing the homogeneous transformation, theta 1 should not appear in the picture because theta 1 corresponds to frame 0. We are in frame 1. So it should be theta 2. Everyone understood this? So theta 1 should not appear because this relationship is only between frame 2 and frame 1. And frame 2 and frame 1 are only related by this angle, which is theta 2. Some of you may ask me, why am I using x0, y0, z0 and theta 1? Why not theta 0? It's just the sign convention in robotics. So that is exactly how I taught, how I was taught. And when the books that you refer, they start with the 0th frame and theta 1. So that's why it's not theta 0, it's theta 1. But this is going to become A4 cosine theta 2, A4 sine theta 2, and then you have A3, and you have 1. Do you agree with me? A4 cosine theta 2, A4 sine theta 2, and A3. Now, if I want to solve the forward kinematics problem, I need to find out overall homogeneous transformation. What is overall homogeneous transformation? 0H2 is equal to 0H1 multiplied by 1H2. So what it means is this one gets cancelled, and finally I land up with 0H2. Everyone understood this? Now let's extend the logic. 0H2 is going to be a 4x4 matrix. So it's going to have 4 rows and 4 columns. It's going to have 4 rows and 4 columns, 0H2. There will be 1 here, 0, 0, 0. Now, after we do all this multiplication, I want you for a minute to look at this representation. This representation, I'm going to write this here. This is 1 R2. And this is the displacement relationship. So can I say that this is going to be 0 R2? And then I'm going to have X position, Y position, and Z position of frame 2 with respect to frame 0. So this, and what is this? This is nothing but end effector position with respect to 0. So can I say this would be X end effector, this will be Y end effector, and this will be Z end effector. Everyone understood this? Forward kinematics problem. We will repeat the exact same process for different robot configurations, and I will solve 3 or 4 more problems till you guys get comfortable. So this is the process. I can do this matrix multiplication by hand. But why we do it by hand when we have MATLAB? Now what I'm going to do is, I'm going to take you to MATLAB and I want you to open the script that I uploaded. Everyone, please open the script. That script is a symbolic script, which means you are going to do symbolic manipulation. So make sure you have symbolic calculation toolbox installed. Now, here is what I'm going to do. I'm going to solve this matrix multiplication by MATLAB. Once I solve matrix multiplication, do you agree with me? I will get an expression that involves A2, A4, cosine theta, sine theta, all that mumbo jumbo, and then that will be at this location. That would be at this location, and that would be at this location. Everyone understood this? Looking at the robot geometry, you agree with me that Z end effector is nothing but A1 plus A3. Because that is the distance from 0th frame to the second frame in the Z axis. Just look at the kinematic diagram we have drawn. So that is a sanity check. So if I want to find out, as you can see that A1 and so the Z position of the end effector ZEE is nothing but A1 plus A3. And let's work this problem out. Now what we are going to do in the next step, and I will walk you through the code. Please understand, this code is going to be the building block for all the forward and inverse kinematics problems that we are going to solve in next class. And you will use the exact same code to solve your robot digestion assignment. Before I go on to the code, any questions about how the homogeneous transformation is set, how the angles and the distances are represented? Anything? Okay. Now, what we will do is, once the forward kinematics problem is solved, we are going to solve the inverse kinematics problem again using MATLAB. Please understand, inverse kinematics is an entire chapter in the textbook. Okay, we'll finish it in maybe one line of MATLAB code. So, because I studied all these techniques to solve inverse kinematics problems. They are not fun. So we will solve inverse kinematics problem using MATLAB. Okay. So what I'm gonna do is now I'm gonna open MATLAB. I'm gonna open forward and inverse kinematic script. I will have to share my screen. Now I will walk you through the code line by line so that you understand. So in this configuration, we are trying to solve R parallel R robot. The first revolute joint is parallel to second revolute joint. You can extend this to as many R robots as you want. So if you want to extend this, you can actually create a worm robot. So basically you can have servo, 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 and basically you can create a worm robot. Now let's understand line number 2 is we are clearing all because we don't want anything in the memory. Line number 3 is I'm defining symbolic variables. So symbolic variables means you don't have to supply a numerical value. MATLAB can treat that value as a variable. So it's like X, Y, Z. You don't have to specify a number. So symbolic variable theta 1, symbolic variable theta 2, symbolic variable A1, A2, A3, and A4. So those are the 4 symbolic variables for the joint link lengths, and 2 symbolic variables for joint angles. Now H01, this is the homogeneous transformation matrix. Cosine theta 1 minus sine theta 1. So MATLAB's sign convention is you cannot assign a variable starting with a numeric value. It means you cannot have a variable 0h1. MATLAB won't like it. So I have defined the variable h01, but it means 0h1. Similarly, I have defined h12, that is 1h2 matrix. Can you compare? Can you see that these matrices make sense? Now, what I want you to do is, I want you to just run this much code. Don't run any more code. Just run the code up to line 2. Run the code up to line 2. Line 15. Now, can you, and I want you to go through this code and see that this all did its multiplication, it all did its simplification, and I want you for a minute look at the result. This is H02. This is the relationship between the second frame where the end effector is located with respect to the 0th frame, which is the fixed frame. Once again, this is 0h2. 2 is the location of the frame at the end effector. 0 is the location of the first fixed frame. Do you agree with me? Then what you have, and it's extremely important that I want you to look at this matrix. This matrix is cosine theta 1 plus theta 2 minus sine theta 1 plus theta 2 sine theta 1 plus theta 2 cosine theta 1 plus theta 2. So this first 3 by 3 matrix is nothing but the rotation matrix. Do you agree with me? And since we studied all this, you agree with me that this rotation matrix has a structure cosine theta minus sine theta, sine theta, cosine theta. You agree with me? Then can you tell me what is the theta in this case? It's theta 1 plus theta 2. Do you agree with me? So what does it tell me? It tells me, very important, frame 2 is rotated with respect to frame 0 by angle theta 1 plus theta 2. Are you with me? Once again, this first 3 by 3 matrix defines the angular relationship between the frame 2 and frame 1. And this angular relationship simply tells me that frame 2 is oriented by angle which is theta 1 plus theta 2. Very simple to see. This is your first revolute joint. This is your second revolute joint. Imagine the total orientation is theta 1 plus theta 2. So theta 2 and theta 1. Do you agree with me? That's what this tells me. The next part, it tells me the x end effector position, y end effector position, and z end effector position. Do you agree with me? And you can immediately recognize that what you see here and here, these are the exact same relationships that I wrote down on the 2 degree of freedom planar robot. So can you see A2 cosine theta 1 plus A4 cosine theta 1 plus theta 2. A2 sine theta 1 plus A4 sine of theta 1 plus theta 2. And finally, since frame 2 is at distance A1 plus A3, so this is its Z position. Everyone understood this? This is the solution of forward kinematics term. Everyone understood this? And I want you to relate this with the 2 degree of freedom planar robot that I just derived. And I will share that with you. So you will see here that this distance is its x component, this distance is its y component. Everyone understood this? Are there any questions here? Yeah. Why is it A4 cos theta 1 plus theta 2 and not just cos theta 2? Right. Why? Because look at the way we have defined theta 2. Theta 2 was defined with respect to link 1, not with respect to horizontal x. Okay. I don't know if you, that is the, because we need to be consistent. Okay, once again, what I mean by that. This is your first joint. This is your second joint. Okay. Now, what I have said is this is your theta 1. You agree with me? So you have cosine theta 1, sine theta 1. You agree? And then I have theta 2. but theta 2 is defined with respect to this length, not the whole angle. And that's why when you solve the problem, you have cosine theta 1 plus theta 2. Because length 2 is oriented not by theta 2, but by theta 2 plus theta 1 with respect to horizontal lines. Any further questions? Now the next part is really tricky, so pay attention. I solved this forward kinematics problem. Now what I want to do is, I want to use this forward kinematics solution to find the joint angles, which means I would supply value of xe, I would supply value of ye, I would supply value of ze and find out what are the values of theta 1 and what are the values of theta 2. Okay, this is two variables, theta 1 and theta 2, two equations. So it should be straightforward. Unfortunately, they are sines and cosine terms. It means you have multiple solutions possible. Sine 0 and sine 180, they are one and same. So you will have multiple solutions possible. That's why we need to make sure that we are using appropriate solver. There is a geometric way of solving this problem. The geometric way of solving the problem, the way I solve, is you can square the terms, add them together, and use the trig identity sine square theta plus cosine square theta is equal to 1. Simplify, represent cosine into its equivalent tangent angles. So tan theta by 2, sine into tan theta by 2. And that gives you a very complicated quadratic equation that you have to solve and then find out the values. If you use MATLAB, MATLAB has built-in solvers which will solve this equation numerically very quickly. However, there are some things that you should be aware of, and I'll discuss with you what you should be aware of. Now let's look at the next thing is what I want to do is I want to capture these equations. So the final matrix that I have is H02. I need to find out end effector x position or Px, position x, position y, position z, position x, position y, position z. So H02, first row, fourth column, first row, fourth column, first row, fourth column, this is my Px. First row, second row, fourth column is my Py, and this is my Pz. So I'm capturing from H02, first row, fourth column, second row, fourth column, third row, fourth column. So that way it will give me these equations. So I will click and say evaluate. And can you see that it gave me a very nice expression? Px is equal to something, Py is equal to something, and Pz is equal to something. Do you agree with me? Now, the next part is typically if I give you some values, maybe value of A1, value of A2, value of A3, value of A4. So these are the robot lengths. Say A1 is equal to 100, A2 is equal to 100, A3 is equal to 135, A4 is equal to 165. I give you theta 1 is equal to 0 and theta 2 is equal to 35. MATLAB needs angles in radians. So I have converted those angles into radians. So what I'm going to do is I'm going to use something called as subs command. Sub stands for substitution. When you use the sub command, what it will do is it will substitute theta 1, theta 2, A1, A2, A3, A4 by these angles T1, T2, A1, A2, A3, A4. Why did I do this? Because if I want to find out multiple forward kinematic solutions, I can just run that in a loop and then I can find out multiple forward kinematic solutions. So I am substituting the link lengths, I am substituting joint angles and finding out the values for Px, Py and Pz. So that is this substitute function. VPA stands for variable precision arithmetic. So that we'll get numbers, not long fractions, but we'll get numbers which are meaningful, small. You are welcome to take that VPA out and you'll get an output which is like fractions, the long fractions, or maybe you will get ratios. So what I want you to do is, I want you to run this part of the code. And once we run this code, can you see you are gonna get X position, you are gonna get Y position, and you are gonna get Z position. So you get Px, Py, and Pz. Important to note, for every value of theta, you will have Px, Py, and Pz. Now the issue there is that this is just a mathematical calculation. So whatever value of theta you substitute, it will give you an answer. But the theta that you are going to substitute must be realizable, which means the actual robot to be able to achieve that value of theta. You probably have noticed your robot magician locks at certain angles. So if you substitute the angles which are outside the operating region for the robot, it will still give you the answer, but that won't be the correct answer because the actual robot won't be able to reach that forward kinematic solution. Everyone understood this? Now, what is inverse kinematic solution? With inverse kinematic solution, I'm going to substitute this. I'm going to say Px is equal to 235, Py is equal to 94, and Pz is equal to 235. Tell me values of theta 1 and theta 2. Everyone understood this? That is going to be the inverse kinematic solution. And that is the next part of the code. So if you go down, the next part is inverse kinematics. In inverse kinematics, I want you to look at, and please understand, we are studying this entire chapter on inverse kinematics with just one line of MATLAB code. Code, basically you would use solve, which is a MATLAB solve function. So it will pick up the right solver to solve the set of equations numerically. So now understand, this syntax looks complex, but it is not. But please try to understand every parenthesis in this syntax, extremely important. If you miss the parentheses, you are not going to get the correct answer or MATLAB will not work. What is the idea? So you have an equation. You have an equation that is equated, double equal to sign, to a number. Px nu is a number. I am asking MATLAB solve function to find out, to solve these three equations simultaneously. So I would actually go through this code and explain it to you. So first, you have this Px, and I want you for a minute to type here Px. Type on the on the command line px. So px. And when you type in px, what do you get? You get an equation which is in terms of variables. You agree with me? So what that line is going to do is px is in terms of these variables. I'm substituting those variables using some dummy variables so that the MATLAB works. I'm equating it to the value of px new. I'm equating that to the value of px new. So what I'm trying to say here is in this equation, value of A4 is given because it's a robot linked length. Value of A2 is given. Value of A3 is given. Value of A1 is given. So I'm replacing A1, A2, A3, and A4 with the actual lengths of the robot. A1B is a number. A2B is a number. A3B is a number. A4B is a number. So this equation would get written as maybe 100 A4 multiplied by this number plus 200 multiplied by this variable. That is equated to px. Same thing I'm going to write for the second part, which is do the exact same thing. Subs py is equal to py new. And I want you to understand, it's extremely important. Please note, since z, xz does not include theta 1 and theta 2, you do not need to include that equation while solving this problem. Everyone understood this? Your xz is not dependent on theta 1 or theta 2. That's why I'm just solving two equations and finding the values of theta 1 and theta 2. So run this code. Run this code and evaluate. Can you see? It gave you multiple solutions. And if so, do you remember what were our initial angles? Can you see it gave us one angle 43 and minus 35, which is the lower configuration, and other is the 0 and 35. So in this inverse kinematics solver produce two solutions, and now you need to check out of these two solutions which is the right solution. Everyone understood this? So this is how an inverse kinematics solver works. Everyone understood forward and inverse kinematics? Any questions? Okay, if you go down the script, the next script is MATLAB code for R, perpendicular R, parallel R. R, perpendicular R, parallel R. Can someone tell me what type of robot is this? This is your robot magician. Everyone understood this? So next script that we are going to look at, and I'm not going to jump onto this script immediately because I need to set up this problem. I need to find out the rotation matrices. I need to find out homogeneous transformations, and then I have to solve forward and reverse dynamics. So in the assignment, that I have asked you, the first two parts is basically substituting the right value for A1, A2, A3, P1, P2, P3, and then you'll be able to solve the forward kinematics problem. Everyone understood this? So what you need to do to complete the first two questions of the assignment, and I promise you this, I will derive all these homogeneous transformations. In one case, you will get the projection matrix which is not aligned. You will work on that. But if you want to solve the first two parts of your assignment, what you need to do is you need to use the Dobot CAD file, or you need to go to Dobot documentation and find out the distances between each and every frame. Everyone understood this? You'll also realize that the way that Dobot is made is not, it's like you don't have revolute joints which are perpendicular. What you have is you have the 4-bar mechanism, which is actually acting like a link. But logic remains the same. We don't worry about how the robot is physically constructed. For example, shoulder joint is a spherical joint. But for us, this joint is nothing but 3 revolute joints attached perpendicular to each other, but they are coinciding. So if you have a 3-dimensional, basically that is how you would do. You would actually separate that. So I would encourage you to take a look at this code real quick. And then please note that first you have the first matrix 0H1. Then you have the second matrix. Then what you have is you have the third matrix. Then you are multiplying 0H1, 1H2, 2H3. So you are getting the relationship between the end effector frame and the zero frame. We are going to find the forward kinematic solution. So here is what you will do. You provide Dobot certain angles. And now by now you know how you can use Python, or you can use Locky, or you can just send commands to Dobot. So you would supply some angles, and then you will find the end effector position. If your coordinate system and the Dobot coordinate system is the same, then your forward kinematic solution must match with the values that are given by Dobot. What is the coordinate system Dobot is using? If you look at the Dobot map, Dobot uses the right-hand coordinate system. If you look at the Dobot map, X for Dobot, Y for Dobot is defined. So it could be different in comparison with the X's and Y's that I have defined here. It means your X, E and Y, E could be flipped. So make sure that your coordinate system is consistent, your link lengths are consistent, and you would get the correct answer. Everyone understood this? So I have about 7 minutes. What I'm going to do in next 7 minutes is I'm going to set up the kinematic diagram, and I'm going to find out the homogeneous transformations. Once I find out the homogeneous transformations, you know the drill. Just use the code, solve for the forward kinematic, use the code, get the inverse kinematic. You agree with me? Okay. Okay. Now what I have is I have R. Remember, the robot that we are trying to solve is R perpendicular to R. So bear with me for a second. What I did. For some reason, it's not switching. Sharing screen. No, not. Yeah, no idea. For some reason, Zoom is giving me. Okay, I will have to stop share this. Okay, good. Finally, thank you. Okay, so I have this first revolute joint. Then I have this second revolute joint. And then what I have is I have this third revolute joint. First revolute joint, I have the second revolute joint, and I have the third revolute joint. So I will set up the coordinate system. So this is gonna be your Z naught. This is going to be, I'm gonna call this X1, X naught. I will also call this my Z1. I will call this Z2. And then again, I will call this Z3. So you have Z1, you have Z2, and you have Z3. This is your end effector. Now you have this X naught. Now I have a choice. So I want you to look at this first frame. This is my 0th frame. This is my first frame. Now, should my X1 go upwards or should my X1 go in the right or left direction? So please understand, I know my Z1 is along the joint, but I have choice for X1. Choice for X1 is I can have X1 here or I can have X1 here. Now for a minute, I want you to think about this possibility of X1. Do you notice that this, even though it seems like it's going through Z naught, we want our X1 to be intersecting and perpendicular. So this X1, so this choice of X1 is not a good choice. So this is not a good choice. So I can choose X1 something like this. Or I can choose X1 going towards right. So it doesn't matter which choice you have. So this could be your X1. Now, second thing is I need to choose X2. And for X2 also, I have two choices. I can have X2 going up or I can have X2 going side. Now, if I choose my X2 vertically, please note this guy is not going to intersect Z1. X2 is not intersecting Z1. So that's not a good choice. So I would go with this as my X2. And lastly, I would have X3 in the same direction over here. Now, I would not use this as X2, X2, X2. So I defined my X0, X1, X2 and X3s. I have my Z0, Z1, Z2 and Z3s. And I can write my Y. So right-hand coordinate system. And I don't think I can finish this problem, but let me set up the coordinate system and we'll start. This is your X. This is your X, Y, Z coming towards you. So you have X, Y, so X, Z, Y going in. X and Z, Y going in. Y0. Now you have X, you have Z. Can you see Y going up? Y1 going up. Y1 going up. Can you see Y2 going up? And Y3 going up? Do you agree with me? Now, what is the most important difference between the previous problem and this problem? Tell me quickly. Can you see that my frame number 3 is aligned with frame number 2? Frame number 2 is aligned with frame number 1, but frame number 1 is not aligned with frame number 0, which means your projection matrix is not going to be an identity matrix. Everyone understood this? Please note, this frame is not aligned with this. So the projection matrix between first frame and second frame would be identity. Projection matrix between the second frame and third frame would be identity. But the projection matrix between the 0th frame and first frame is not going to be identity. That's the only difference. I'll stop here. But to attempt the first two parts of the assignment, you don't need the homogeneous transformation worked out. I will work out this problem again in next class. But that should not stop you from solving first two parts of the problem.